the general formula is y would equal yc plus yp. So let's first work out yc, which is probably the easiest one than yp. And that's going to be looking at this as if it's a quadratic. So like y squared minus 4y plus 4. So we can then just solve it. If we replace this for, let's say, p, you're going to get p squared minus 4p plus 4. This y disappears because you're essentially dividing everything by dy dx, or in a different example that I've shown in a different video, we divide everything by e to the power of something. I'll probably link that in the description below as to why this disappears, but I'm not going to go over that in this video because that's a whole other video. And then this would, that means, be factorized into p minus 2 all squared, which equals 0. So therefore, p would equal 2. The solution for the homogeneous equation for yc is yc c1 e to the 2x plus c2 x e to the 2x. So this is a general formula, and we're going to put in the values that we get. So if let's say that's 2 and 1, you would then put 2 and 1 in here. So we've now got yc. We now want to start working out what yp is. So this is when we bring in the Wronskian. So the Wronskian is of y1 and y2 is where you let y1 equal e to the 2x and y2 equal x e to the 2x. So we're going to substitute those two in, and then that means our general formula is w y1 y2 with respect to x, which is going to equal y1 y2 y1 differentiated and y2 differentiated, which is equal to, let's now substitute all of this in, e to the 2x x e to the 2x, and then if we differentiate this once using the chain rule, you're going to get 2e 2x. You differentiate this using the product rule, because obviously there's two parts. It's going to be 2x e to the 2x plus e to the 2x. And if I put a little circle around that. And then we're going to calculate the determinant. Calculating the determinant of a 2 by 2 matrix is quite simple. You multiply this by this minus this times this. So we're going to have the determinant of w, which is e to the 2x, 2x e to the 2x, plus e to the 2x. And now we're going to minus that from x e to the 2x multiplied by 2e 2x. So we've got that. We can now simplify. So this is going to become e to the 4x, 1 plus 2x minus 2x. And then obviously we can simplify this fully. So we're going to then get e to the 4x. So that means the Wronskian with respect to x is e to the 4x. We now need to find out what w1 is, so the Wronskian of one part, and w2, which is the Wronskian of the second part. To do this, we're going to have w1, which is 0, y2, the function, and y2 differentiated. And the Wronskian w2 is going to be y1, 0, y1 differentiated, and then the function. So this is all with respect to our right hand side we're dealing with. So if we want to substitute everything in, you're going to get 0, x e 2x, x e 2x, and you're then going to get 2x e 2x plus e to the 2x. So that's going to be w1, and then w2 is going to be e to the 2x, 0, 2e 2x, and x e to the 2x. And now we're going to do the determinant for each of these. So if you do this times this minus this times this, you're then going to get w1 to be equal to minus x squared e to the 4x, and w2, if we do the determinant of this, you're going to e2x times x e2x minus this, which is obviously going to be 0. You're going to get x e to the 4x. Bear with me, because now that we've done this, we can move over to the next part. So we need to now work out what yp is, which is u1 y1 plus u2 y2. And u1 differentiated is w1 divided by w, and u2 differentiated is w2 divided by w. Lucky for us, we have all of the values for w, w1, and w2, so we can then plug it in to this to find out what u1 and u2 is. Obviously, we're going to integrate our answer for this, and then we've got yp. So let's start doing that. So you're going to have u11, which is equal to minus x squared e to the 4x, all divided by e to the 4x. And u2, the differential of it, is x e to the 4x, that's here, divided by e to the 4x. So obviously these are all going to cancel out, and you're then going to get this as minus x squared, and this as x. We're now going to integrate this, so u1 would then become the integral of that. I'm not going to put all the symbols and everything. It's going to be minus the third x cubed, and then this integrated, so u2 is then going to be x squared divided by 2. So we can now plug all of this into here. So let's now put that in. So yp is going to be minus a third x cubed, and then where's our value for y1, which was e to the 2x. We've got y1 here, it's e to the 2x. And then we add that to u2, which is x squared over 2. And we're then going to put in y2, which was x e to the 2x. So now we have yp. However, we can simplify that a bit further. So that's going to become a sixth x cubed e to the 2x. So we've now got yp, but remember at the beginning we had the equation y equals yc plus yp. So y would then be yc, which was c1 e to the 2x plus c2 x e to the 2x plus, and we add this yp, a sixth x cubed e to the 2x. You could leave it like that. You know, this e2x is a common, so let's pull that out, and that means you would then get c1 plus x c2 plus a sixth x cubed. And now you've used the Wronskian to successfully solve a non-homogeneous second order linear equation. Pretty straightforward, steps to learn. Doesn't matter what the questions are, just repeat the same steps and you should get the correct answer.